Morning, everyone. My name is Xu from Northwestern Polytechnic University. It's my pleasure to attend this symposium, and I will talk about particle transport and deposition in washout thermal turbulence. Okay, first, a few words on the background. There are frequent sandstorms in northwestern China, particularly every spring, like March or April. And there is widespread dispersion of these sand particles in the atmosphere. From the perspective of fluid mechanics, there are two types of atmospheric turbulence that influence the sandstorm dynamics. One is this shear turbulence caused by the horizontal wind speed gradient. And the other is the shear thermal turbulence that's driven by the vertical temperature gradient. Okay. And in fluid mechanics system, for the shear turbulence, we have so-called the model system, wall-sheared channel or quiet channel that describes the horizontal motion of these flows. For the wall-sheared flow, it's driven by the body force, and for the quiet channel, it's driven by the wall shear. And for the thermal turbulence, the kinetic flow system is really Banach convection cell, which describes the vertical motion driven by the temperature difference. And when they combine together, we have so-called wall-sheared really Banach system, or the quiet really Banach system. And normally in the atmosphere, the friction Lewis number that describes the shear strength can reach as high as 10 to the power 7, and the bulk Lewis number can be as high as 10 to the power 9. And for the Rayleigh number that describes the buoyancy strength, it can reach as high as 10 to the power 18. However, the relative strength of buoyancy over shear strength described by the Richard number is in the order of 1. That means in the atmosphere, usually the shear and the vertical buoyancy, they are comparable. And there are also a lot of works have been done for study particle transport in the shear turbulence system and in the thermal turbulence system. And our focus is for the particle dynamics that simultaneously encoded by the horizontal shear and the vertical buoyancy. Now, a few words on the numerical methods. We perform direct numeric simulation, use Boolean approximation to describe the coupled fluid flow and heat transfer. The washout Lewis number is defined using the character length of the height of the flow system and the washout velocity to define this REW washout Lewis number. And the Rayleigh number is in the range between 10 to the power 7 and 10 to the power 9, and the Prandtl number equals to 0.7, corresponding to that of air. And you may notice that our REW and RER Rayleigh number is far below the real atmosphere, because normally DNS is still, the capability of DNS is still far below the real case. And for the particle part, we adopt the point particle model and one-way coupling. This is justified by that we consider a low volume fraction, normally less than 10 to the power -5, and a small particle size. Our particle size over the Kolmogorov length scale is less than 1/6. Okay, now I'm present you the simulation results. First, I'll show you what is the flow field. That means there's no particle. Okay, and here shows the contour or temporal fields, and this is the case for the REW equals to 0, which means this represents the connected Rayleigh Banach convection cell. It consists of two large rows in this aspect ratio. And when we increase the washout strength, in the 2D case, the large scale rows will undergo horizontal expansion and eventually leading to the transition to this so-called zonal flow state. This is particularly for the 2D case. And in the when we do the 3D simulation, okay, and REW equals 0, this is conventional Rayleigh Banach convection. There's thermal plumes, and when we increase the washout strength, it will transform into this thin straight, these streaks. Okay, eventually when the shell strength is very high, we observe these streamwise oriented rows. Notice that this our streamwise oriented rows is different from that in the pure channel flow, because in the pure channel flow, this streamwise oriented row is just a near wall small scale structure. And in our case, this streamwise oriented row, it spans the whole handle chat, which means that is a very large scale structure. And this can be more evidently visualized if we plot to this time average streamline. Okay, in this case, the last one you see REW equals to 4,000. You see this very large scale spanning the whole height of the streamwise oriented row. And now I just quickly show you a movie. Okay, oops, the movie doesn't work. Okay, I intended to show you the movie, but seems it doesn't work. Okay, I'll skip these two movies. Luckily, I have another slide. Okay, this just takes instantaneous snapshot, but I intended to show you a movie. Okay, these are for the case of small Stokes particle number case, and for when we see small particle number Stokes number is the particles are either have a small density or has a small diameter. In this case, we can see that all the particles are randomly distributed throughout the whole convection cell. There is a little or no aggregation, both for the 2D case and the 3D cases. And when we increase the diameter of the particle or we increase the density of the particle, we come to the so-called the medial Stokes particle. And we observe that there are more particles in the upwelling regions and few particles in the downwelling regions. Okay, this movie works. And we want to understand why there's more particles in the upwelling regions and relative to the downwelling regions. And also to confirm our observation, here we plot the wall deposition locations for the particle. We can clearly observe that the peak in the probability density function of the particle distribution along the horizontal wall locations. Actually, this peak corresponding to the rising plume, hot rising plumes, in this movie. And we propose the following mechanism for what happens here. When the particles, they are advanced to the low boundaries by the downwelling flows, they are entered by the fast horizontal motions, and the circulation edge and transport back into upwelling regions. That means in these upwelling regions, the probability of deposition will increase. For the large particle size, we further increase the particle size or particle density. It becomes much simpler. Just the particle, for what become nearly unresponsible to the carrier flow. They just fall along the vertical direction. Now the second part I want to talk about is the particle deposition on the wall. And previously for the small particle, small Stokes number particles, which means either small density or either and small diameter. These particles behave like a flow tracer. And almost 30 years ago, there's work that proposed an experimental deposition rate for these small Stokes particle numbers. And for particles with a large Stokes number, we can just imagine they are heavy stones, and they follow a linear deposition rate. They almost unresponsible to the carrier flow. This is so for the actually derived from the classical Stokes drag law. And now our question is, how about for particles with medial Stokes number? For a small Stokes number and a large Stokes number, there are two extremes. There are already very established theories. But for medial Stokes number, because the interaction of particle turbulence is very complex, so actually there are no very good theory on this. And now, before studying the medial Stokes number, we first validate our DNS results with this and two extreme the theories for a small Stokes number and a large Stokes number, we can see our DNS result agree with this exponential deposition rate and the linear deposition rate at these two extremes. And now, what about the medium Stokes number? Now, in this middle column, we present you the DNS result. These circles represent the DNS result. And based on our DNS result, we propose that the particle deposition stage can be divided by a first linear stage, followed by a non-linear stage. And we mark this transition time as TS. Okay. Next, I will explain what exactly happened in the linear stage and what exactly happened in the non-linear stage. Okay. To answer this question, because we already have our DNS result, we can do the posterior examination of the particle initial deposition, which means that we check which particles deposit in the linear stage. Okay, here marks the positions, which means that in these fingers, the particles in this position, they will deposit in the so-called linear stage. We can see that the particles in the linear stage, they are mainly in the low domain of the convection cell and the downwelling areas. We can also present the particle trajectories. We can see that for particles deposition in the linear stage, their height will decrease monotonously and they will not recirculate in the convection cell. And based on this standing, we propose the following model, and we adopt the so-called particle drift equation, because even for our largest Stokes number, it is still far less than 0. This is different from the HIT, homogeneous tropical turbulent flow, because in our case, is the particle will act under the gravity. So even for the largest density and the diameter, it is still, the Stokes number is still less than 1. We can adopt the particle drift equation. And for particle subject to updraft and downdraft, we can write their velocity. And we assume the same portion of particles will be affected by the updraft and the downdraft. And we can eventually end up these two particle numbers and calculate the deposition ratio. Here, N0 is the initial particle in the convection cell. We can see that the formula is indeed a linear function of time. That's why we call this linear stage. And what happens in the nonlinear stage? Similarly, we can use our DNS results to do a post-run examination. And for particles deposited in the nonlinear stage, here is their initial position, and they are mainly in the row center and upwelling areas. And we also provide the typical particle trajectories. We can see that they circulate within the row. And however, due to some irregularity, they will escape and eventually deposit on the wall. This is for the nonlinear stage. Okay, then we, based on the idea of stochastic, we propose a stochastic deposition model. We denote the time duration for the particle to complete the circulation as Tc, and its probability that escape from circulation as lambda f, and we can obtain the particle number suspended in a convection cell, and eventually write their deposition ratio. Here in our model, there still are no parameter C1. Okay, C1 and C2 here. Later on, I will show you that it can be fitted by DNS result. Now, a brief summary of our model. We divided the deposition stage as the first linear stage, followed by a later nonlinear stage. Okay, and now we have still some unknown parameters C1 and C2 here. To determine these unknown parameters, we assume that it's smooth settling curve. Okay, this is very intuitive understanding because the particle deposition will not have a sudden transition. Okay, we assume it's a smooth consistent curve, which means until the TS, they should be equal. Then we can write C1 as a function of C2. And then our unknown parameter left is TS and C2. And to obtain this TS and C2, we can use our DNS result to do the data fitting. Okay, these are our proposed some empirical correlation for this DNS data fitting. Now let's see how our model works. Okay, and in this plot, okay, the left column is the small Stokes particle number, and for the right column is the large Stokes number, and medium is for the medium Stokes number. Although our motivation is to predict the medium Stokes particle segmentation, we can see that our model also applies for the small case and the large Stokes number cases. And particularly for the median Stokes particle number, in this plot, okay, this red line is our new model. This dashed black line is the previous model that reported in the 2020 PRF paper. We can see that our model can be more accurately agree with the DNS result. The accuracy and some places can even increase as high as 50%. Okay. We also calculated the particle mean resistance time. Okay, we can see in the for this medium Stokes particle number particles, they have a longer mean resistance time because they will circulate within the large scale circulation. Okay, summary of my talk today. We studied the particle transport under the combined effects of vertical buoyancy and the horizontal shell. And we propose a mathematical model that describes the particle deposition with an initial linear stage followed by a later nonlinear stage. And this work was published last year in JFM paper. Co-author includes my master students, Mr. Benrui Xu, and my team leader, Professor Han Dongqi. Okay, thanks for your attention. I'll take a couple questions.
Okay, thank Professor Xu. Do we have any questions from the audience? Yes.